Welcome back to ECE 441A, 541A. We have arrived, fall has arrived, I guess, by the temperature. It's a little bit cooler here in Tucson this morning, but that gets us ready for the homework and exam. Homework number 7 is due on Wednesday. Exam number 3 is this Friday, and lab 3, and if you're in 541, the project, those are due at the end of the first week of December, essentially. Question? So the project is described, the question was, what is the project about? The project is described on D2L. I would allow you to read that description and then come ask me if you have questions. So I think it's easier for you to read it and then formulate questions for me rather than for me to try to describe it right now. I'm debating on how to put that out there, but I think it's okay right now with respect to the description online. So look at that on D2L and see if that is clear, and if it's not, then we can discuss that one-on-one. Today what I want to do is really go through an evolution of different controller designs. And we'll do that with our particular mass spring damper system, or one of the possibility of mass spring damper systems. We'll look at what it does in the open loop, why we would want to change that. We can change the dynamics with a phase lead controller, and maybe the phase lead controller won't give us all that we would like. Maybe it does speed up the system response, but now maybe it does not give us the tracking or the steady state accuracy that we would prefer. That leads us into PID controllers, which all of this is what you will do really in lab number 3, and I'll try to step through some of that with the Matlab scripts that I have available to you for executing lab number 3, and I'll do some of those today as we're walking through these designs. Then we will get into designing controllers to actually stabilize unstable systems. And now we may start putting poles and zeros in the right half plane. But remember, what are we not doing with poles and zeros in the right half plane? You're not canceling any other poles and zeros. You can put poles and zeros over there, but just don't use those to cancel poles and zeros in the right half plane. That's what really is a no-no. So let's now get started with this controller design evolution. Here is A, not our. You may not have this system, but here is a representative mass spring damper system that's somewhat like what you might have in your system in the lab that you're working on. Here, the denominator, I have it written as a factored complex set of poles. Your poles are at -2 plus, whoops, that was your question. Where are the poles located in this system? Is it clear from the factored form that that's written in that we do have poles at -2 plus and minus J20? I now know what happens if I put S equal to 0 in the denominator. I get a constant, and that constant is going to be 2 squared plus 20 squared. So I factored that out of the numerator constant, and now I can explicitly identify my DC gain. What's my DC gain for this system? The gain is now 12.3. And that's what you get when you evaluate that transfer function at S equals 0, at DC. That's the DC gain. If we sketch the poles, of this system, and this won't be to scale. I don't believe this is 20 times or 10 times that distance, but you hopefully get the idea that we now have a fairly small real part relative to the imaginary component of those poles. That's our system, or a system, and that's the system that we will play with today to illustrate some of these design concepts. If somebody asks you to sketch the root locus for that system, now you're just applying a gain, k, and adjusting that gain k from 0 to infinity. What's the root locus of that system look like? Is everybody clear on what that looks like? What's your pole 0 excess? That's 2, isn't it? So that gives you now this fundamental angle, 180 divided by 2, or 90 degrees, and now you have odd multiples of that fundamental angle spread around your entire S-plane. You now have an asymptote going off at 90 degrees and another asymptote going off at 270, or I might just say plus and minus 90 degrees. The centroid of that asymptote is simply centered right underneath that, or right in between, or with the same real part as those two poles, and your root locus then would be marching off in the positive and negative vertical direction as you increase the gain k. What's that going to do to your settling time? How will, if you now increase the gain k in a closed loop, what's that do to your settling time? What's that do to the settling time if you increase the gain k in this closed loop configuration? Sigma is not changing, is it? So the settling time is not changing. What will happen if you increase the gain k and move along that root locus in the closed loop? What properties of your system will be impacted? So the peak time, now your natural frequency, and really the damped frequency is what's you can really see is the piece of the natural frequency that's changing. So omega sub d is increasing. Your peak time, you'll get to your peak quicker, you'll have more overshoot, and now that may influence your steady state error, but you're not going to enhance your settling time at all by introducing a gain. So let's now look at what we might obtain here by just looking, and I'm going to call this open loop behavior. Suppose that we now have our K sub PF we have our system that we've now identified above as that two-pole system. Here is our reference, and let's say that that's now 2,000 counts. And in this case, I'm going to have 0 for my feedback, and I would like to know what's going to happen to the output Y. This is what I would consider open loop. We have nothing being fed back. Where are my poles? I would sort of consider this as the k equals 0 scenario, because you're not closing the feedback path. Now your poles in this system are right where the poles of G of S are. They're not influenced by that gain of 0.075, and they're not influenced by that applied reference input of 2000. If we now look at what this might do in terms of Matlab, let's now define our transfer function. That, what did we say it was? 4,969.2. And the poles, if we multiplied it out, we're at s squared plus 4s plus 404. That's now my transfer function for the system. I'm going to actually put in a particular time index. I'm going to sample at 5 milliseconds. My time, I'll just call T1, is going to go from 0 up to, let's say, 4 seconds. And now Y1 is going to be 2000, a scaled version, times 0.075 times the step of G1, using time T1 as my time horizon. And I don't want to see all thousands of data points. I'm going to follow that with a semicolon. Now I can actually plot that and see this response that maybe looks like something that you saw in the lab when you excited your system and go to 2,000 counts, and now is it reaching 2,000 counts? It's not quite, is it? It's a little shy, and we could actually look and see some of these data points. This is one of the nice things with Matlab. You can say, give me one data point, go graphically, so get a graphical input. Who knows if I'm going to be able to do this very effectively with this mouse, but now I have crosshairs, and I could actually go and find that peak. And the peak now, let me say that the time of peak, TP1, is actually the answer 1,1. Answer was ANS, that's the default variable, and that's where I clicked. Let's see where that was. That was at 0.1613 seconds. And the maximum value, let's say that it was P1, is now equal to answer 1, 2. That was at this 3,180. That was where I peaked, or that particular response peaked, and it peaked at 0.16 seconds. I could then, if I wanted to, find the settling time. You can eyeball the settling time. What would you say the settling time is? 2% settling time. Maybe a little bit more than 2, 2.5 maybe is a reasonable settling time for that system. And we could do the same technique. We could say get another graphical input, just one. That's what that one is for. And let me just see where I ended up in terms of my steady state value. And my X steady state of this open loop system is now at 1,837. And I could now compute my percent overshoot from the peak and the steady state and get some value if I wanted to. But maybe that's not what I want. Maybe that particular behavior is not quite what I want. I want a faster settling time. And we've said that we could get that by using a phase lead controller. So this gave us, let's say, a settling time of approximately 2.5 seconds and a percent overshoot, which was some value that we could compute. We could say the P01 was equal to, what did I call this? P1 minus XSS1 so about a 73% overshoot was what we had in that particular system, and a settling time, let's say, of about 2.5 seconds. And I could go with a graphical input and try to improve that. But now I want to speed up the response. Which means I want to move those poles further into the left half plane. And I can do that. I now have poles here and here. We know that zeros like to attract the root locus, the branches of the root locus. So if I simply put a real 0 here, and let's say that I could do that without putting a pole in, which I can't do. I can't just put a 0 in. I have to accompany that with a pole factor so that I don't just do differentiation in my analog signal processing. I want to roll that off. But now do you see what the root locus would be for this configuration of poles and zeros? What would the root locus look like? Do I have any French bread? Do I have any real line segment that belongs to the root locus for this particular pattern? And this pattern is not final, but just to get a feel for, can I pull the branches of the root locus over to the left further than -2? We have wherever I located that 0, let's say this is now at -z, I'm going to have that segment is going to belong to the root locus, because I have an odd number of poles and zeros to the right of any point to the left of -z. What's my pole 0 excess? Just for this sort of thought process, I'm thinking through this. What's my pole 0 excess? 1. How many asymptotes do I have? 1, and it's at -180. These two poles would come around here. One would go there and one would march off there, and that would be the behavior that I would see if I could just adding a 0. That's not realistic, but it helps our insight. Meaning, well, I kind of like what's happening here. Could I just put a pole quite a ways to the left and it would sort of be similar? And that's what we're really going to do with this phase lead. You could now say, let me now get more realistic. I now have, and this is why it's helpful to know the root locus rules. I now have to put a pole to the left of that 0 to make a realizable transfer function. Now what does the root locus look like? Do I have a segment of the real line that's on the root locus? Do I have 2 segments, 3 segments, or 1? I have 3 divisions of my real line, don't I? I've separated my real axis into 3 segments. I have a right segment, a middle, and a left. Is the, okay, so here's a thumbs up or thumbs down. Is the rightmost segment a part of the root locus? Up or down at the count of 3? 1, 2, 3. Okay, so the rightmost is not. What about the middle segment? 1, 2, 3. The middle segment is between the pole and the 0. The middle segment of the real line is between Z and P. So now I'm asking, is this segment, does that belong to the root locus? And I think I saw quite a few thumbs being up, and that's true because we have, what, an odd number of poles and zeros to the right of any point in that interval. What about the leftmost segment? Up or down? 1, 2, 3. Okay, good. So everybody better get that question right on Friday as far as cutting the bread. Okay? And where does the root locus live? Pardon? 90 out of 100. You'll at least get 10 points out of 100 if you get that question right, right? So you get 10% at least. You want to start on a positive note. So this guy is coming there. And what's my pole zero excess? 2, which means what kind of asymptote angles do I have? 90 and 270, don't I? And depending on where I pick that Z and P, that's going to move the centroid, but let me just guess. I'm just going to put something in there and say it's right there. And now what's going to happen? These poles are probably going to do something like that, based on where my 0 and pole are located. And they are moving to the left, aren't they? That's giving me a better sigma on those 2 dominant poles. How many poles am I going to have closed loop? How many closed loop poles will I have with this compensated system? I want to see fingers at the count of 3. How many closed loop poles am I going to have? 1, 2, 3. And I gave it away by saying I'm counting to 3. I should see 3 fingers. I have 3 open loop poles, and I have 3 closed loop poles. Depending on where I put my gain, or select a gain, I am going to have these at complex conjugate pairs, and that third pole is going to be approaching that 0. Now, what we have then is we have this phase lead design that has some structure where the 0 is closer to the imaginary axis than the pole. And we want to find our 0 and pole location. We could do a lot of analysis, but maybe we want to speed this up by a certain amount. Let's just plop that 0 down at 10, at -10, to try to pull that over. So now let's say that this is going to be -10, and just so we don't spend a lot of time on this today, because we really don't know exactly where that root locus is going to go until we pick that pole. Let's go ahead and make that pole at -30. So now we have a fair amount of separation between the 0 and the pole, and let's see what might happen with respect to this design. And I actually have a Matlab script that will do this, and it's p-lead. Yours may be p-lead, it may be p-lead 3. I don't know what I put on D2L. I was playing with this yesterday, so now I think I have a p-lead 4. That's phase lead 4 is what that stands for. Now, this asks you some questions to basically walk you through this design. First question is enter the numerator constant for our system. And this is set up to be specifically for this pure two-pole system for lab number 3. And this was 4,969.2, I think, is that what it was? So 4969. Now it says enter the denominator polynomial for the system, and it's wanting this in the form of a row vector. The leading coefficient was 1. The linear coefficient was 4. I had s squared plus 4s plus 404. My constant coefficient is 404. Now I'm trying to build up my phase lead controller. It says if the 0 is at s equal minus z, enter the value for z. It's wanting a positive number for z. So z equal 10 is what I said I was going to use, and that puts my 0 at minus 10. I'm going to put in a 10. And now it says enter the phase lead pole location, and I said I wanted that at minus 30. So let me put my, I hope this is where I wanted those to be. Now I want P is equal to 30. And this is the root locus that results from that pole 0 pattern that I have with a phase lead, a 0 at minus 10 and a pole at minus 30. And it does do that behavior that I suggested in terms of the root locus pattern. Now what it's going to do is it wants you to hit the enter key. And once you hit the enter key, it's going to execute a root locus find command, which is sort of like that graphical input. It now puts crosshairs on your root locus, and you get to pick where you want your poles to live when you hit your mouse button. It's going to say, oh, I want to be on this spot of the root locus for my closed loop poles, and it will tell you the gain to get you to that spot. Meaning, if I now hit enter, now I have crosshairs, and if I wanted to be maybe about right there, right above that 0 with respect to one of my closed loop poles, the other one is going to be the conjugate, and then I'll just have to figure out where the third one is based on that gain selection. And you don't have to be that accurate. This now puts you in the ballpark. This now says that a gain of 0.43, and do you see the plus signs, the red plus signs? That's actually where you would be, or that's where I clicked, and for that gain, then I'm going to have a closed loop pole at about minus 15, and the others are going to be at minus 10 plus or minus J47. Whew. Okay, but this is a phase lead controller. Now it says, well, if you weren't real happy with that gain, or if you were, just pick a gain for this controller. Let's say that I pick a gain of 0.4, just for grins. It's close to what I found from that design. And this is now the result of doing that. This is now the closed loop system behavior with that phase lead controller, a gain of 0.4, and here's your transfer function for the phase lead controller, 0.4s plus 4 over s plus 30. What's the settling time here? Yeah, I would even say 0.6 maybe. That's better than 2.5, isn't it? So I have sped up my system response. I have accomplished that with my phase lead controller. I still have a tremendous amount of overshoot, don't I? Because I had a lot of imaginary piece to those dominant poles. If I go back here, this P lead will actually tell me my closed loop poles are at minus 9.8 plus and minus J46. I have another pole at minus 14. My settling time is 0.43. My peak is 2.3. My percent overshoot is 90%, so now I'm worse than the open loop, but I could see that because of where my dominant poles were located. But this is maybe not what we want to, you may not want to go into your boss and say, oh, I've designed a phase lead controller for your system, and your boss, she might say, what's your steady state accuracy? And you go, well, I wanted to go to 2,000 and I made it up to 1,242. And she might say, well, that's not quite what I want. I would like you to be a little closer than an error of 800 counts when you're trying to get to 2,000. And that's then what motivates the next phase in this evolution of design. Let's now look at building up a PID controller. We've introduced this. We have a proportional piece, we have an integral piece, and we have a derivative piece. And if we put all of that over a common denominator, we have k sub d s squared plus k sub p over k sub d s plus k sub I over k sub d. Or we could think of that as some gain and a combination of two zeros. That's our PID controller structure. Or you could have complex zeros. What happens in this particular case? Suppose now this is our S-plane, and we're doing back of the envelope thinking. Here are our plant poles. With the PID controller, we now have placed a pole at the origin, and I could create two complex conjugate zeros if I wanted to. For what reason? Why would I do that? What's going to happen to the root locus? Do you see what the root locus pattern is going to be for this pattern of poles and zeros? Do I have a real axis segment on the root locus? Is it on the right or the left of the imaginary axis? It's on the left, isn't it? So I actually have, what's my pole zero excess? 1. So I've actually reduced my pole zero excess with this ideal PID controller. I've introduced one pole and two zeros. That's now reduced my pole zero excess behavior of the system. This guy is probably going to just march off there, and these two are going to approach those finite zeros. That's now the root locus pattern for two zeros that are complex conjugates. I could pick two real zeros. again, I'm forced to have that pole at the origin. Now I have a type 1 system. I now have one pure integrator in my combination of system and controller. Suppose now that I pick a couple of zeros that are real zeros. Maybe this is minus C1 and this is minus C sub 2. What's the root locus look like here? There's a piece of this real line that's on the root locus. Between my zeros is not, and to the left of minus C2 is. This will probably just go that way, and these are going to move around. One will approach that 0 at minus Z sub 2. How many closed loop poles do I have? Just counting the x's, right? And I have 3 branches of the root locus. For some particular choice of gain k, and I think in lab number 3, I just tell you to pick a particular zeta value, not a percent overshoot, just a zeta value for the complex poles. And I think I say something like, make zeta bigger than 0.7. What's that mean for those triangle locations? The angle now needs to be, how is it related to 45? If zeta is 0.7, we know that that corresponds to an angle of 45. I want zeta bigger than 45, or zeta bigger than 0.7. What's that mean for the angle? Is it going to be less than 45 or bigger than 45? If zeta is getting bigger or closer to 1, I'm going to have a smaller angle. So now I'm wanting to be inside an angle of 45 degrees with those triangles and the origin. I need their real part, their distance into the left half plane now needs to be longer than the distance to that triangle vertically. And that would give me a zeta value bigger than 0.7. Is that clear? And then I will have a third pole right there. So let's do this with Matlab. And this one I'm calling PID 2. Again, I need to enter the numerator coefficient. I'm going to forget the fraction, 4969. The denominator was 1, 4, 404. Is that what it was? Okay. And now enter the PID controller 0 polynomial. What I'm meaning here is if I actually picked, let's say Z1 was equal to 10 and Z sub 2 was equal to 20, then this is going to give me an S plus 10 and an S plus 20 in the numerator, or an S squared plus 30S plus 200. And so my polynomial that I'm entering into Matlab for that particular numerator polynomial of my controller is going to be 1, 30, 200. My 0 polynomial then is 1, 30, 200. And now do you see that I could have picked complex conjugate zeros? I would just have to multiply them out and get this second order polynomial and put in the appropriate coefficients if you wanted to pick those that way. Here's the 0 polynomial, and there's the root locus. Does that look consistent with what we sketched on the back of the envelope? Pretty close, isn't it? It is what we sketched. Now, we can do the rlocus find, R-L-O-C-F-I-N-D command in Matlab, and it will ask for us to locate with the cursor or with the crosshairs the point that we want to select our gain at. And again, I have to hit enter to get it ready to do that command. And now what I'm looking to do is if I'm 40 into the left half plane with my poles, then as long as I stay here, if I went here, is that satisfying a zeta greater than 0.7? Is it clear that I'm not satisfying my zeta condition? I need to have my real part bigger than my imaginary part, and if I come over here, let's say to minus 40, whoa, then a gain of 0.0166 is, let's see how close I made it, is right there. And you can see where the other plus sign is between the origin and minus 10, that 0. And that's going to also influence my transient behavior. I now have a third pole. I have 2 zeros. So I have a 3-pole 2-0 system. All of those are obviously not a pure 2-pole system. So I have to take those formulas or those design specs with a little bit of hand waving. Now, let's enter a gain for the PID controller. We're pretty happy, I think, with that location. So let me just go ahead and say that I'll pick 0.0166, and that's now my response, which if I go back to Matlab, see that sort of gradual tail as it goes to the steady state? That's the influence of that third pole that's near the origin. This particular PID now says I have poles at minus 39 or minus 40 plus and minus J27. That gives me my zeta value that I wanted. My third pole is at minus 7. That's going to influence my slow behavior at the tail. My settling time is 0.35. My peak, I now have a percent overshoot of 8%. My peak was occurring at 40 milliseconds. Where was my, oh, my settling time was 0.35. So now I'm getting sort of the benefits that I wanted. I'm getting a reasonable overshoot. I'm getting a quick response. My settling time is pretty fast. And what's my steady state accuracy? Well, it should be 0 because I have a type 1 system. That type 1 system, that pole at the origin, now gives me this type 1 system. And if I have a constant input, I'm going to have 0 error due to that constant. So I get 0 steady state error, I get a reasonable overshoot, and my transient is acceptable. But that's obviously not a pure 2-pole system response, is it? It kind of has this tail to it that's gradually approaching, although it's not that gradual relative to the original open loop design. Are there questions on the PID controller? What if you had to find the gain of that controller on an exam? We did it with Matlab. You're not going to have Matlab on the exam. I'll just let you know that right up front, okay? So you don't have Matlab, but you do have Matlab during the lab. Lab 3 is basically we just performed in today's class. But suppose that you now had to find the gain case of D. We have G of S, our system was this 4969 over S plus 2 squared plus 20 squared, and our controller that we used was this k sub d, let's just say s plus z1, s plus z sub 2, all over s. And now somebody says, I want you to put your closed loop poles, one of them right there. How do you compute k sub d? This is now minus z1, this is minus z sub 2. You're going to have quite a few lengths to calculate, aren't you? You have the distance from that pole to that location. Let's call that LP1. We have the length from the pole at the origin, which is coming to us because of the PID, the pole in our integrator. Let's call that L sub P sub 0. We also have this distance to compute. Let's call that L sub P sub 2. And we have the distances from these two zeros, LZ1 and LZ2. Where k sub d is now this expression, this is just the magnitude condition. We have s plus 2 minus j20. We have s plus 2 plus j20. And we have s plus z1, s plus z sub 2. And we can't forget our constant downstairs. That formula is just setting the magnitude of our controller and plant equal to 1 and solving for k sub d. Where this magnitude here was LP0, this is LZ1, this length is LZ2, and what's this first length? Z plus, or S plus 2 minus J20. It's either L sub P1 or L sub P2. So now that one corresponds to what value of S? Let S be such that that factor vanishes. What's the value of S that makes that factor vanish? It's minus 2 plus J20, isn't it? So that's the one that's up in the second quadrant. This length corresponds to the shorter distance. This is L sub P1, and this is L sub P sub 2. And we would evaluate that at S equal to S delta. Is it clear where or how you could do that on an exam? If I said you need to locate your pole at this point, you could then calculate all of those distances. You could do it with a ruler, you could do it with dividers and a ruler, or you could do it with your calculator and compute all of those right triangles and find the hypotenuse of all of those right triangles. You would have to know where that S delta was physically to do the computation with your calculator. But if that was at minus 40 plus and minus J, whatever it was, minus 40 plus and minus J 27, you could compute those lengths. And we did the length calculation graphically with PID 2 in Matlab. And it came out to be 0.0166 to give us those values. Are there questions on this process? Wednesday, what we're going to do is figure out how do we sprinkle poles and zeros in the complex S-plane if somebody gives us an unstable system. We've looked at phase lead. We've looked a little bit at phase lag with a PI. We've now done PID, which is another way of thinking of a lead lag controller. It's giving you both steady state accuracy and transient behavior all in one. We'll pick up with stabilizing unstable systems on Wednesday.